Let's look into the Kruskal's algorithm. So the Kruskal's algorithm is used to find a minimum spanning tree. So it has a similar goal as the Prim's algorithm. So, uh, and this works for connected weighted graphs. So the algorithm aims to find a subset of the edges that forms a tree that includes every vertex, and the total weight of all the edges is the of the tree is minimized. So that's another goal of the algorithm because it's looking for minimum spanning tree. So the way the algorithm works is initially the graph is not connected. So it finds a minimum spanning forest at the beginning because it starts looking for the edges of the smallest weight. So a forest is basically, you can call that a collection of trees. So a minimum spanning forest is going to be basically a collection of minimum spanning trees, right? But the eventual goal of the Kruskal's algorithm is to create one minimum spanning tree. So, um, and we'll look at the algorithm how it works. So Kruskal's algorithm is an example of a greedy algorithm. It makes the locally optimal choice at each stage, right? And the main goal is to find the global optimum result. So if you look at the algorithm here, on step one, we create a forest in such a way that each graph is a separate tree. All right. Now we create a priority queue, and that is used for implementation purposes, that contains all the edges of the graph, all the edges of the graph. And the reason why it's a priority queue is because the edges here has a weight. So the queue works in a way. We know that a queue is first in, first out, and a priority queue is the highest priority items are queued out first. So if two items has the same priority, the first one which was inserted is chosen. So the same step works here. So we can have many edges with same weights or different weights. So we insert all those in the priority queue and we dequeue one by one, and then we start creating our minimum spanning tree. So step three is basically a loop. It says that repeat step four and five while the queue is not empty. All right. So we're going to repeat step four and five. That is basically our loop here. So at the very beginning of the loop on step four, we remove an edge from queue. So we dequeue the priority queue and we get one edge. So if the edge obtained in step four connects two different trees, right? This is very important. It has to connect two different trees, then add it to the forest. All right. Now, one thing that I want to point out, if you have just two nodes, all right, this is also a tree. Okay. So that means it is important for this algorithm to understand. So for combining two trees, and the reason why this step is because it at first creates forest or small trees, and then eventually connects all of them together. So it is important to combine two trees into one tree. And the edge that is obtained for on step four, if it does not connect to different trees, which are so so if we have multiple edges which are connecting one tree, and if we choose the first step, then we all then the two trees are connected already. So it is one tree now. So if you have a second tree of that same of another edge which was previously connecting those two trees, we're not going to select that. So for those cases, we just discard the edge and we do not consider that. And we repeat this process until Q is empty. All right, so now I'm going to simulate the Kruskal's algorithm, and we're going to see how the algorithm actually works. So at first, we create the priority queue. So here I have put all the edges of the graph in this priority queue. and I want to talk more about it. So it's not just a queue, it's a priority queue. So the priority is basically the smallest weight of the edge. So the if you look at all the weights of the edges, the weight here, which is CE, is the smallest one, which is 1. So CE goes in first, then comes in AB because it has a weight of 2. Next is we got weights of 3 in 3 different edges: AD, AC, and also BE. So if you look here, and you can insert it in any order. It doesn't have any order. So I've inserted AD, AC, and BE on that order. You can have that in any order because they have the same weight. Then comes in BC because BC has a weight of 4, and we have only one of it. Next one is CD, which has a weight of 5. So we put in CD here. Then we have DF. So the weight for DF is 7. Then we have EF. The weight of EF is 8. And then finally, the edge GF, which has a weight of 9, is inserted in the priority queue. So that's how we construct the queue first, and then we dequeue the queue and run the algorithm until the queue is empty. So now let's have a look at the first step, actually the second step. So here, at first we dequeue the queue. So we get A minus, so we get CE because it was in the queue first, and we remove that from the queue. So it's not here in the queue anymore. So after our dequeuing process, now we're going to look at the CE itself. So CE connects, the question is, does it connect to distinguish or two different trees? So it does. C is a single node, E is a single node. So you can consider those as trees, individual trees, which has just one node. So C is connecting them. So we take that. C is here, and we add this to this forest. It's a forest because that's what Kruskal algorithm works on. So the next one is we dequeue the queue again, and we get A minus B. So let's have a look at A minus B. It has a weight of 2. It is connecting to distinguished trees or two different trees, which are not repeated in the forest. And so we put it here in the forest. At the moment, they are not connected because it's a priority forest. And we'll proceed with the algorithm and see how whether finally it creates a forest or not. Where it can eventually connect all the nodes and create a tree, which is still a valid answer. So now we dequeue the queue again, and we get A minus D. Sorry, AD, not minus. We get AD. So AD is connecting two different trees. The answer is yes, it is connecting two different trees. So we add it to the forest. So this is how our forest looks like now after adding AD to the forest. Then on the next step, we dequeue the queue again, and we get A minus C. Again, sorry, as AC. So AC, the question is it connecting two different trees? The answer is yes, it is connecting two different trees because previously we had two different trees which had A and C in it. Now it is connecting two different trees together. So we put it in the forest. On the next step, we dequeue again, and we get BE. So now we ask the question, does BE connects two different trees? The answer is no, because B and E are actually parts of the same tree. So it is not connecting two different trees. So we do not consider that. We do not put it in the forest. Next, we dequeue again. So we get BC, and then we ask the same question, does BC connects to different trees? So we already have B and C here on the tree, so it is not connecting to different trees. So we're not going to put it in the forest. Next, we dequeue again, and we get CD, and we ask the same question, does CD connects to different trees? So in our tree here, C and D are not connecting two different trees. It is those two are now part of the same tree. So we are not going to put that in the forest. Next, we DQ again and we get DF. DF, we ask the same question. Does DF connects two different trees? The answer is yes. Um, F was not present here. So D and F is connecting, DF is connecting two different trees. So we put it in our forest. Next, we DQ again, we get EF. We ask the same question. Does EF connects two different trees? The answer is no, because E and F both are part of the same tree. So we're not going to include that in our forest. Next, we again DQ the Q and we get GF. So we ask the same question. Is it connecting to different trees? So the answer is yes, it is connecting to different trees. And there's a problem here. It's going to be G. I have it wrong here. So it's going to be G. Let me fix that real quick. So this is going to be G, not F. So G and F is connecting to different trees. So we include that in the forest. So that is the end of our algorithm because our queue is empty now. So we go to the next step. So here, this is the tree that we just formed. So you can see that if you rearrange that, it kind of rearrange the tree to look like a traditional top-down view. We get this. It's the same tree as this one. We just rearrange the nodes for visual reasons. So now we can calculate the total edge of this minimum spanning tree, and we just put all the numbers of the edges here and then sum it up. So we get 25. That is the total edge weight of the minimum spanning tree when we run Kruskal's algorithm in this.